So I want to continue talking about errors for finite series here, because again, this is going to have an effect when we start talking about whether an infinite series converges or not. The last video I talked about how we can bound the error, in other words, find the largest error for a geometric series that's finite, what we called the truncation error. In this video, I want to talk about the more common error we deal with, which is if we're working with a Taylor series, and instead of an infinite Taylor series, it's a finite one. In other words, when we're working with Taylor polynomials. In that case, we call the error either the remainder, or we can also call it the Laplace error. Uh, and the idea behind remainders with Taylor polynomials is we know a Taylor polynomial is an approximation. It's not perfect. So if we had an n-order Taylor polynomial, remember n is referring to the highest degree of the terms, as well as which derivative we're using of the function, and dividing by that factorial within that highest degree term. The remainder would be, what if I wrote one more term for this Taylor polynomial? So if I had an n order, the n plus first term is our error. So that's either, you can call it the Laplace error or you can call it the remainder. The one thing to note here is instead of using the center to plug into that n plus first derivative, we're using some value c that's between the center and the x that we're interested in. And as we do an example, that c will make a little bit more sense. So to bound the error of a Taylor polynomial, we want to focus on the n plus first term of our Taylor polynomial. In other words, what the next term would be. And the reason we want to focus on this and just that one, instead of like with a geometric series working with an infinite series that's remaining, is if I were to do the limit of this remainder, if I call the remainder r sub n of x, if as n goes to infinity, my remainder approaches 0, in other words, as I add more as I get larger and larger terms, my remainder shrinks as I do it, then my infinite Taylor series will converge to the function for whatever our interval is for x. And generally speaking, in order to make our math a little bit easier, we try to do this with the absolute value of our remainder. Because if we can show the absolute value of the remainder converges, then the entire series must converge even without the absolute values. And it's a concept that's known as absolute convergence. So an example I want to do here is actually our Maclaurin series for cosine of x. So here I have cosine of x, and we're going to show that this converges for all real x's. So remember, the Maclaurin series, the center is 0. So just to make a note of that, a is 0, the center. And we're saying that this is going to converge. So that means that my remainder, if I do the limit as n goes to infinity, should approach 0. So there are kind of three things we want to look at here. We have the x minus a to the n plus first power, which is an exponential. And what we need to keep in mind here is because it's an exponential, x minus a to this power is increasing if x minus a is bigger than 1, and decreasing if x minus a is less than 1. It's the whole idea of exponential growth and decay. We have the n plus 1 factorial. This is a factorial. What we know is no matter what is happening to the x minus a to the n plus 1, the n plus 1 factorial is growing faster. So the whole idea of it is this term right here is shrinking down to nothing because of the n plus 1 factorial. So what really determines everything is the n plus first derivative for some value of c that's within our interval of convergence. So it's really what happens to the derivatives that's what we care about. So if we're dealing with cosine of x, well, we know the derivative of cosine is negative sine. Second derivative would be negative cosine. Third derivative is sine. Fourth derivative is cosine. And we just keep cycling through positive and negative sines and positive and negative cosines. So this is one of the reasons why it's really nice to have absolute values, because then all we really care about is what's happening with sine and cosine. Well, we know the domains for sine and cosine are both all real numbers. And if we're talking about the absolute values of those, we can even say the ranges are between 0 and 1. So what I want to do with this derivative here is, because I'm trying to find the largest that my error could be, I want the biggest that this could be. So if we're talking about what's happening with our function, with our remainders here, I know that whatever my derivative is, it's going to be something between 0 and 1. I know that a is going to be 0, so this really I could just write as x to the n plus 1 over n plus 1 factorial. Well, if I'm choosing the biggest, and again, I want the biggest that the n plus first derivative could be, I would say if it's between 0 and 1, the biggest could be is 1. So I know that my absolute value of my remainder has to be less than or equal to 1, the biggest my n plus first derivative could be, times the x minus a to the n plus 1 over n plus 1 factorial. So if this goes towards 0 as n goes to infinity, then my remainder is going to 0, which means that this series will converge to cosine of x. And it's actually, if we think about it, that's what we're going to be doing, taking the limit of each side of this. Well, if we were on this side, we already said that factorials grow faster than anything. So it doesn't matter what x minus a is. N plus 1 factorial is growing faster, so that limit is going to 0. Since we're talking about absolute values, that forces our limit of the absolute value of the remainder to equal 0. Therefore, the series converges to cosine of x. And we did nothing to talk about the domain to restrict it, so this does converge for all real x. Now, as far as how this can actually work in practice, let's say we were using x minus x squared over 2 to approximate the natural log of 1 plus x. And we want to bound the Laplace error, in other words, figure out what's the largest the error could be if the absolute value of x is less than 0.1, or in other words, if x is between positive 0.1 and negative 0.1. Well, looking at the series, I can see I'm not subtracting anything away from x, so my center is 0. So this is really a Maclaurin series. And, whoops, sorry about that. And so if I'm thinking about this, I can also see the degree is 2. So my error is going to be the next term, the third degree. So my remainder, when I'm at degree 2 of our series, will be the third derivative for some value c over my n factorial, but my n is 3, so over 3 factorial, times the x minus 0 to the third power. And again, we're going to deal with the absolute values of these to make our math a little bit easier. And if this works with the absolute values, then we should be good. All right, so then I want to deal with this third derivative. Well, we know the function is the natural log of 1 plus x. The first derivative then would be 1 over 1 plus x. The second derivative would be negative 1 over 1 plus x squared. And the third derivative would be 2 over 1 plus x cubed. Now, the general shape of this, if I'm going, oops, if I'm looking between -1 and 1 for the x's, -0.1 and +0.1 for the x's, is my graph is going something like this. Kind of like what we just talked about with the cosine and Maclaurin series is, I want to choose a value here. The c is going to be wherever my derivative is largest, because I want to know the largest error. Well, the largest f triple prime value is at x equals -0.1. So that's what I'm going to use for c. I'm going to use -0.1. So by doing that, I can now say that this is going to be less than or equal to the absolute value if I plug -0.1 into my derivative. So that's 2 over 1 minus 0.1 cubed times my x cubed over 3 factorial. But what did I just plug in for x? I plugged in 0.1, so the absolute value of my remainder is going to be less than or equal to the absolute value of 2 over the 1 minus 0.1 cubed times -0.1 cubed, because that's what I plugged in for my x, over 3 factorial. And what I get when I work that out is that my remainder is going to be less than or equal to 0.000457. So as long as we're within 0.1 of 0, our little quadratic here gives a really good approximation of the natural log of 1 plus x.